Good afternoon, everyone. Welcome to the last class of reagents in organic synthesis. In this class, I am going to discuss about samarium-based reagents and ytterbium-based reagents. So both are lanthanide-based compounds. So lanthanide compounds are very important compounds. They have been used in many chemical reactions in organic synthesis and chemistry. So samarium, one of them is the best useful compound for the carbon-carbon bond formation reaction by single electron transfer pathway. So in this case, I'm first going to discuss about Simon-Smith type cyclopropanation of allylic alcohol by samarium-based reagent. So this is allylic alcohol. So allylic alcohol under samarium and dimethyl iodide or diiodoethane. So in the presence of diiodoethane and samarium, it can form cyclopropane, just like Simon-Smith reaction. So Simon-Smith reaction, what happens in this case? CH2I2 plus zinc copper combination is from the zinc carbenoid, which react on the enone or allylic or alkene generate the cyclopropane. So what is the mechanism here? So samarium means presence of diiodomethane from the samarium carbonate. So this is the samarium 2 carbonate which react onto the allylic alcohol and generate the cyclopropane. So this is the mechanism. So this is the allylic alcohol. This is the most stable intermediate. So if we see, so this there are no steric indents, no steric indents are there. So what happened? This is the CH2 samarium and this is the samarium carbonate which react onto the this alkene and generate this cyclopropane. So due to the coordination of this alcohol with the samarium and this CH2, so the cyclopropanation happen from the same phase. Cyclopropanation happen from the same phase. So if the alcohol is onto the upside or beta, so due to the coordination of samarium and this samarium cyclopropanoid carbenoid, so the cyclopropanation happen from the beta phase. So if this is the beta, so here is the ratio is very high. This is 5:1. The beta is the major one and the alpha is the minor one. So if we use methyl CH2I2, there is two possibility. This methyl can be alpha or beta. So the enantiomer is 5, the diastereomer is 5:1 dear. So in these cases, this is beta. So beta is the major, greater than 200:1. So this mercury used to elevate the reaction. So this samarium and mercury facilitate the reaction more. The yield is improved. So in presence of mercury, the reaction timing is also improved. So this is the cyclopropanation product. Now, if we use LDA and samarium compound, samarium and diiodoethane, so what happens in presence of LDA, lithium diis? So what is LDA? Lithium diisopropyl amine. So this is base. Lithium diisopropyl amine. What happens in these cases? This base, this is the ionizable proton, acidic proton. So base abstract one of the acidic proton and form the enolate. So this is the enolate which will form. Now this alkene under samarium carbenoid undergoes cyclopropanation. CH2 samarium. So this is coordinate like this way, and this cyclopropanation happen. These are some example. So here it will form this enolate. Here it will form this enolate, and here it is from this enolate. And giving this cyclopropated product. So one of the important reaction of samarium iodide. So here I am going to discuss about the samarium iodide chemistry. So this is a single electron transfer reaction. That is the deprotection of the toluenes. So it is the ester. So tolu. This is the toluenes. This is toluene. Toluene carboxylic acid. This is the ester form. So this is toluenes. So the protection of toluenes is also possible in samarium iodide. So this is a single electron transfer process. So samarium is the plus 2 form. So it's transfer one of the electron to the carbonyl or ester. So it will form this one. O minus samarium 2, or it will form samarium 3 after giving one electron. OR1. This is the toluene. Now if we use this R1 like this way. Now there is a possibility of homolytic or hetero cleavage. So this is the homolytic cleavage. The single electron will form. So this is the radical. It will go O minus, O radical, this radical plus R1 prime radical. So this radical and this radical form ketone. O minus. So it is under solvent or water, it will generate the acid. Toluic acid will form, and here this is also captured if we use methanol, so it proton and form this RH. So this is the deprotection of toluenes is also important in samarium chemistry. So by this way it will deprotect. So here after toluene deprotection, so it will form homolytic cleavage will happen. So this is from this radical and this samarium toluene complex, and which under protonation giving this product. So now I am going to discuss about activation samarium iodide mediated activation of halides and carbonyls. So this is the very important reaction, very important reaction. So samarium iodide activate both halide if there is a alkyl or allyl halide, or carbonyl if there is a ketone or aldehyde. So ketone, between ketone and aldehyde, the reactivity of aldehyde is faster, or between iodide and bromide or chloride, the reactivity of iodide is much more greater than the bromide and chloride. So what happened in these cases? The samarium transferred one of the electron, and this single electron transfer happen and generate this R dot radical. So this R dot radical further react in presence of suitable electrophile. If we use unsuitable electrophile, so this form R electrophile compound. Or if we use water, it will protonate it. Base same that samarium also transfer one of the single electron to the carbonyl compound, It will form this radical. Further, this radical can be trapped. This is one electron given, then it will form this O minus. This carbon negative will form. So it can be trapped either in presence of any electrophile or either H plus. So it will form electrophile samarium hydro. After hydrolysis, it will form the alcohol. Or if it is use only water, so it will give this alcohol. Now I'll discuss about the reactivity. So first is the samarium mediated Riefer-Matsky reaction. So this is the alkyl halide. So under samarium iodide, so it will single electron transfer happen and generate this radical. So it will react onto the carbonyl center. This is the acceptor and generate methyl O. So this is accept over samarium one electron transfer here and generate this O minus, and it will abstract proton and give this alcohol. So one more mechanism is possible. So samarium can also transfer single electron to the carbonyl. So it will give O minus methyl, this one CHO C double one two CH2Br. So now this will can further react and divide with the bromo, giving this intermediate. Further single electron transfer from one samarium, giving this negative charge. This will abstract proton and give this product. Maybe yeah. Sorry, I was wrong there. So this will form this one. Single electron transfer happen here and generate this negative charge. One samarium give electron and form this negative charge. This is samarium. Replace. It's a two type of reaction happen, giving this one. Further proton transfer, produce this alcohol. So here is the radical alkene cyclization. So first single electron transfer and cleavage, giving this radical. Giving this radical. Now this radical react with the alkene. Forming this radical. So this take one electron from the samarium and bombing this negative charge. It will use D2O. So it will abstract proton from the D2 and giving this D and incorporated furan. Now I'm going to discuss about carbonyl alkene cyclization. So carbonyl is a carbonyl. So in presence of samarium, to giving one of the electron, single electron to the carbonyl. This is the radical and this is O minus, and samarium after giving one electron will form samarium 3. So this is the intermediate. Now this is radical cyclization happening from here. This this will give this will give this radical. So after proton transfer, it forming the alcohol, tertiary alcohol. So now I will discuss about samarium mediated pinnacle type reaction. So first carbonyl samarium give one electron to the aldehyde. So between aldehyde, carbonyl and ester, first it will react with the aldehyde. And from this radical, so this will coordinated with this ketone with, to activate this. Now this radical react and generate this one. So this will further protonation giving this diol. As the coordination happen with the samarium and this ketone, so this is the cis diol will form. So both the alcohol in the same group. Now I'm going to discuss about the ytterbium chemistry. So ytterbium catalyzed cycloaddition reaction I will discuss. So this is the imine and this is the diactivated system. This is electron donor, electron donating group. This is electron withdrawing group. So now in presence of ytterbium, what happened? C double one, C double one to OR, C double one to OR. So ytterbium is the plus 3 oxidation. So it will coordinate with this oxygen and pushes the electron of this single bond. So this is the donating ER prime. Flip like this way. So it will extract or push this electron pushing from the this side to ytterbium side, and it will form this compound CO2 or CO2 or AR positive. So or this negative charge is stabilized onto the resonance of this the carbonyl center. Now if we add one acceptor, so here this is an imine is the acceptor here. Now it will react in this way or it will react onto the this way and from the six member ring. So this is the product which will form CO2R, CO2R, each here prime. Or either what happens, this lone pair if it is like this way and this will broke and react onto the this center which from this negative charge it will further react onto the carbonyl center and generate first this one. CO2R, CO2R, NPH. This one further, there is a proton, it will shift deuterium coordinate with this oxygen. So then it will block and form this alcohol. Now I'm going to discuss about problems. So first is the cyclopropionation of samarium and diiodochloromethane. So this is the samarium carbenoid will form iodo samarium CH2Cl. Samarium carbonate will form. So the samarium carbonate react with the allylic alcohol. So not with this alkene. So this can be happen through the coordination. Samarium will coordinate, alcohol will coordinate with the samarium. Alcohol coordinate with the samarium. There is a CH2 iodo chloro. So this react this way and this react this way, giving cyclopropane. So react happen from the same phase. So due to the coordination of the allylic alcohol, so due to that cyclopropane will be the same phase. So this methyl remain as such. Double CH2 CH2. Cyclopropane happen from the same phase, either this way. So if it is happen, then it will go on the beta methyl. So here, so this one option, and in this is the A. This is A. What is B? So we have used tributyl aluminum. So just tributyl aluminum and diiodomethane. So this will cyclopropionation happen to the more substituted alkene. So this one. So here cyclopropionation happen with this one. Cyclopropane. With A is this, B is this one. So this is the right answer. A, this is A and this is B. So this is also samarium mediated cycle. So LDA, lithium diisopropylamine, extract the proton or analyzable proton from here, which form this enolate. Now in presence of diiodomethane and samarium, samarium carbonate will form. So this will react and give the cyclopropionation. To realize cyclopropionation happen, and after workup it will give this one. So this is the right answer. Now this is the samarium mediated, samarium iodide mediated deprotection of benzoates or toluenes. This is toluenes. This is benzoates. So what happened? Samarium 2 transfer one of the single electron here, and it is go this, which will form O minus or O samarium 3 compound will form O samarium 3 single electron. This is the adamantane group. Adamantane. Now this is adamantane with single electron transfer happen and adamantane radical will form, and this is with that benzoate forming this samarium 3. Then after proton, this will protonate, adamantane will protonate, and it will form acid. So, and what happened with this one? Single electron transfer, same way, this, and then radically flip, so it will form this radical. After proton addition, it will form this one. So right answer is this one. Now samarium 2 medium. This is alpha hydroxy ketone. Alpha hydroxy ketone. So samarium in presence of alpha hydroxy ketone. What happens? Samarium transfer single electron here with that ketone. Then it will form O samarium 3 single electron OSC. This one. What happened in the next step? What happened in next step? So this OSC will be single electron trans leaving group, so it will leave and generate this O samarium 3 double one switch to I. Now after proton it will abstract, it will form the lead, then this enol form will automatize to keto form. Give this one. So it will give this one. This is beta amine, beta amine, beta amine ketone, beta aziridine ketone, ketone. Same as before, so single electron transfer happen to the samarium and it will form this compound in TS. O samarium 3 after one electron transfer, CH3 radical dimethyl. Now this radical will flip this way. So this aziridine bond single homolytic cleavage happen, leaving this N tosyl radical after one this one OH after samarium leaving. So then ketoenol automerization happen. HCH3, NTS radical and dimethyl, right? Then it will put abstract proton and this will also further tautomerize. So it will give COCH3, CH3, CH3, NHTS. So the right answer will be this one, option 4. Now this is the pinnacle type of reaction, samarium mediated. So samarium transfer single electron here. So it will benzyl, samarium coordinate. This will form. So this oxygen coordinate with the samarium to maintain in the same phase. Now this single electron transfer onto this and moleitic cleavage happen. So it will give 1, 2, 3, 4, 5 numbering 1, 2, 3, 4, 5. Benzyl, O benzyl, OH. Both the alcohol coming in the same phase. So samarium it is coordinated with samarium. So this methyl go on to the down phase or alpha phase. After protonation from the tertiary butanol, so it will give OH, O benzyl, O benzyl, O benzyl, and methyl. This is the pinnacle type of reaction, pinnacle. So the right answer will be the B. Now this is the reduction of the beta activated alkene. So samarium can also react with the activated alkene. So this is the activated alkene acid. So single electron transfer happen from this in presence of activated alkene. So this will go and this will react. So samarium OH. Now this will neutralize and this samarium, one molecule of samarium further giving this generate the anion. So it further protonated giving the saturated system. So this only possible in presence of activated alkene where this pi bond can resonate with the activated group. So this is, but here there is no nothing is there. So no reaction happen. No activated group are there or no reactivity of the samarium. So no reaction happen with the B. No reaction. No reaction. Here it will form this one. So A is this one, B is no reaction. So option D is the right answer. Now predict the following statement as correct. The outer electronic configuration of samarium 2 is 4s7. This is correct. Correct. Select a reduction of aldehyde in the presence of ketone could occur with NaBH4 CCl3 in ethanol. No. So Luche reduction can happen. This is a Luche reduction condition. This is not possible between aldehyde. So this is RCHO. This is cat ketone. If we use this condition, both this aldehyde and ketone reduce to alcohol. Cerium 4 plus is only tetrapositive lanthanide stable in water. Yes. Kangan et al. Reported the carboxylic acid ester nitrile could not reduce by some. Yes, carboxylic acid ester nitrile and ester. I showed the before example, first example, ester under toluenes under samarium condition reaction happens. So ester and nitrile react with the samarium, but not the carboxylic acid. So this is also incorrect. Transilamic alcohol could be reduced with samarium diarrhea HM2. Transilamic alcohol, which is this one. So now this is not possible. This is not activated alkyl. Not activated. Not activated. If it is the activated alkene, then it will reduce. But here no activation is there, so it will not. This is also incorrect. The lanthanide is generated after completion of the reaction constitutable less toxic. Yes, this is correct. So A, C, and F is the correct answer. This one. So cerium 4 plus beta reduction of aldehyde and ketone is selectively is not possible under NADH4 condition. So ester and nitrile reduced under samarium iodide condition. Ester and nitrile can be reduced. Or trans-cinnamic alcohol reduced with samarium. No, this is not possible. Trans-cinnamic alcohol not reduced under samarium iodide condition. So here the meta-halogen exchange happens. So or this will undergo single electron transfer here. In pH2. This will form this radical. So this radical now from this one. 1, 2, 3, 4, 5. 10 minus 10 pH2. Now it will abstract proton from the T chip. So and generate NH NPH2. And this is a consecutive reaction. So it is happened from the same place. So that's why this is the cis orientation will form. Now this is between what happened in this case there in presence of samarium iodide single electron transfer happen. So it will single electron transfer happen and give this radical. So 1, 2, 1, COOET H Cl. This will form between iodine and chloro. Iodine is more leaving group, so first samarium react with the iodine. So now this radical react this one with the ester. So it will 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5. 5 member will form. This will form this page. Hmm. 2 minus. Wait. Page. CH2, 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 CH2. 1, 2, 3, Cl. Now, further, this O minus will pushes the electron and leave this OET as a ethanol. Minus ethanol will form remove. Now it will form this ketone, phenyl, and CH2, 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 Cl. Now, samarium 2 can single electron transfer with this L ketone. So it will O samarium 3 will form and form this radical. Now this is pH. Cl. Did I see something? 1, 2, 3, 5. Oh, after that, it will leave this one single. So this will generate this 5, 5, 5, 5, 4, samarium 3, pH. Both will be the same case. In case of 5, 5, cis is the most stable conformation. Now after proton, it will leaving this one after protonation. Now the right answer is option B. So this is the last question. What is the major reaction? So in presence of aldehyde and amine, it will form imine. This aldehyde after removal of water from this imine. This imine. So if I write like this, this will form. Now what happened? There is a alkyne and ytterbium. CO2 ET, CO2 ET. So in presence of ytterbium, there is a possibility of this is the fourth pi electrocyclization reaction. This is the 4 plus 2 type of cyclization reaction, 4 plus 2. So it will coordinate or activate this ester group, this two ester. Then this lone pair will go. This will react with the benzene and this will this one. So after what happened? Then here one benzene ring. This is the ester. So it will form this one, right? Now, okay. Now aromatization happen. So after aromatization, it will give this product. This one, pH, right here. So quinoline is there. Quinoline, pH, CO2 80, CO2 80. From here, it will cycle and this. Right? This is the right product. So this is the amine one, amine part. This is the amine part, and this is the aldehyde part, which form, and this is the alkyne part. So 4 plus 2, formal 4 plus 2 type cyclization. These are the 10 questions which we have today. So if you have any question, and you can ask me. This is the last class. Otherwise, I will close the session. So in this session, I have discussed about the mainly on the samarium based reagents. Past I have discussed about cyclopropanation by samarium, then Simon Smith type ketone activation by the samarium, then toluene deep protection by samarium, then alkyl halides and carbonyl activation by samarium, then Ricard-Matsky reaction, samarium mediated alkene radical cyclization, samarium mediated carbonyl alkene cyclization, pinnacle type reaction, and then 4 plus 2 type of cyclization reaction by Italian trip. So, okay, then I'm closing this session if you have no question.